Yeah. So you will probably find that I am myself very critical of self-organized criticality. So maybe I should apologize a little bit about that beforehand. Maybe I'm too critical about it. So I'm going to hear from you how you're perceiving the status quo of self-organized criticality. Maybe I'm a bit too pessimistic. Let's see what happens. Of course, I'm happy if you've got any questions to interrupt me at any time. So one reason why somehow Henrik Jensen eagerly suggests me as a speaker because he has written a very nice little booklet about self-organized criticality, and that was very, very well received because it was very, very well written. And a couple of years later, 10 or 15 years later, he was asked by Cambridge University Press whether he would like to write an update. And then he said, maybe not me, but maybe Gunnar wants to write an update. So I wrote an update. It's this book here. And it cost me an awful lot of time in the library. And I then realized that there are fantastically many different perspectives on self-organized criticality, some of which I'm going to highlight in this talk. So I'll show you an overview. I'm going to talk about self-organized criticality. The early program, maybe I should have said past and present, so I've tried to make that a bit more compact. Then I've got a section on universality classes because Pierre asked me to have a section on universality classes. Turns out it's a very, very, very short section because there are very, very few universality classes, and you will see that later. And then I talk a little bit about the theory of SOC. And recently, for the last couple of years, to be honest, I've been struggling with a field theory for self-organized criticality. I think I've got a good handle. I know the action and I know what it looks like, but it's very, very difficult to go through the renormalization process. And it's not a functional RG. It's a plain, good old field theoretic RG with scalar couplings, as you would hope somehow. But you can see everything there, at least at mean field level, everything drops out instantly. You've got the self-organization, you've got exponents, you can see what sort of interactions happen on the lattice, you can check that numerically. So it's a lovely little theory, but I still haven't got the exponents for dimension less than 4. So I'm going to go through this, touch on this a tiny little bit, maybe not at a technical level, similar to the one we've seen yesterday in Kai's talk, a bit more superficial at the level of diagrams. But maybe at the level of diagrams, you can also see particular interesting interactions. So I'm going to go through this fairly quickly and then try to come up with my slightly pessimistic view on what self-organized criticality has to say. Now let's get started. So this is a wonderful picture of the BTW model. I'm not going to tell you precisely how I obtained this picture. It's not very relevant. And maybe it's appealing to some of you. So that's why it's here. Self-organized criticality was the answer, the supposed answer to the question, where does scale invariant behavior in nature come from? And as I said, I've got a slightly different view in it. Maybe one should ask, is there much scale invariant behavior in nature? So it was meant to be the answer to the ubiquity of scaling in nature. And of course, if you're a bit more skeptical, then you ask, is it really that ubiquitous? But anyway, it was a very, very nice answer. There's no doubt about it. It has triggered an immense amount of research, very, very interesting research. And some of it is just inspiring, somehow spin-off ideas. And it's wonderful to see that. There was a bit of context at the time. Some of you might know this really nice article by Anderson, More is Different, which really introduced complexity as a theme. There was 1/f noise around. People were interested in the origin of 1/f noise, and the title of the original Baktang-Wiesenfeld paper makes direct reference to 1/f noise. And Kadanov asked, just a year before Baktang and Wiesenfeld published their paper on self-organized criticality and the first model, which is now known as the Senpai model, Kadanov published a paper asking for the physics in fractals. I mean, The fractal community, fractals and chaos, was in full swing. People were publishing nice little pictures, and Kadanoff was asking the critical question, what is that good for? Bakhtin and Wiesenfeld said, well, here it is. This is the physics of fractals. Self-organized criticality is the physics of fractals. I'm now going to introduce the Bakhtin-Wiesenfeld model, the Sandpile model, as a paradigmatic model of self-organized criticality. The trouble is it doesn't really work that well. In one dimension, it's not overly exciting, and they knew that straight away. And in two dimensions, if you do it numerically, if you analyze it numerically, then you will find that it never really scales properly, and things never really work out well enough, as well as you would hope. But anyway, I introduced it in one dimension, so you can see the key ingredients. So a typical model has a certain number of, say, particles on sites, a discrete number of particles on sites. And there's an external driving that adds a particle. And typically, if something like the slope, which is the height difference between two consecutive sites, if the slope exceeds a certain threshold, then something happens that's called a toppling. So there's a redistribution of particles. In this case, in this particular picture, in this particular representation, it means that particles start going down this slope here. So there's a toppling now happening because the threshold here is 1, and this height difference exceeds the threshold of 1. So one particle is moved to the right, and now the threshold is exceeded at this column. This particle is then moved again to the right, and it rolls through the entire system until it's dissipated at the very end. So you've got the three key ingredients: external drive, internal toppling, and dissipation. And the totality of these topplings, all topplings together by one external driving step, is an avalanche, and there's no driving taking place if there's any activity in the system. So as long as there's any toppling going on in the system, as long as there is any side that exceeds the threshold, then there's no activity and no external drive. And so that's a separation of timescales. I'll get back to that in a second. So initially, in the initial paper, in the 1987 paper, and also in the 1988 PRA, these three authors made direct reference to the existence of long-range correlations. So in space and times, correlations that they maybe want to measure. But it's numerically very, very difficult to measure these correlations. And certainly back in the 80s, it was very difficult. And while there are several reasons, one of them is that you need to have open boundaries. You can't have periodic boundaries. There's no translation invariance. I get back to that actually later. So because of the lack of translation invariance, it's tricky to measure correlations, to get good statistics for correlations. So they quickly resorted to some sort of integrated measure. So you integrate over time and space. Let's say you integrate over time and space activity, and that's then the avalanche size. And avalanche sizes can be measured as, say, the number of topplings, the number of distinct sites taking part in an avalanche, or the duration. If you introduce a time scale, you've got a duration. So all of that statistics can be gathered, and it turns out that the statistics display some power law behavior. Yeah?
Why is it called dissipation? I mean, it
yeah.
resembles a little bit to turbulence, where you have also this cascade of energy transfer, and then you have dissipation. But there it's real dissipation. But here...
Well, the particles are thrown out of the system. That word dissipation, that caused an awful lot of misunderstanding. Initially, it was important that these systems are dissipative, so that in the end, particles are thrown out of the system. And most importantly, actually, the dissipation happens inside the system. Energy is being lost because potential energy is reduced. So they called it open dissipative systems. Well, Hauer and Kada later on called that open dissipative systems. But at the same time, particles in the bulk are being conserved. So there was a time in the early 90s when there was a bit of a misunderstanding, a clash in the literature, where people said, on the one hand, the system is dissipative because you've got a reduction of internal energy. At the same time, it's conservative with respect to particles. So it's really tricky. Nowadays, I think most people call a system like this, where the bulk dynamics of particles is conservative, just conservative. Yeah?
Is this rules that you said is the Oslo model?
Sir?
The rules that you described.
No, that's a BTW model. In the Oslo model, you've got an additional, but that's really the only difference, you've got an additional random choice of the threshold. So after each update, the local site is assigned a new random threshold, and in the simplest versions, either 1 or 2. Okay, so the answer to Kardanov's question, where's the physics of fractals, by Bachtang and Wiesenfeld, is here. This is the physics of fractals. So I show you a quick movie. I've got a couple of movies of different models, and well, maybe you can appreciate that people find this appealing, because while you get these structures and they appear in smaller and smaller sizes, and maybe you can see why people would consider this as some sort of fractal phenomenon. It looks a bit complex anyway. So it's beautiful, and people characterize it. And I think to some extent, the BTW model that has been analyzed to fantastic extent, and there are exact results, really, really, really nice exact results. But as far as avalanches are concerned, I think the BTW model is generally perceived as not really displaying the right behavior. It's not really scaling. It's always slipping away. Right.
You throw grains only in the middle.
Sorry?
You throw grains on a single point in the middle.
Yeah. That's not, I mean, this is not really important. It's just the beauty of this picture. It's just accept that it has some appeal. Okay, so here are a couple of key ingredients for self-organized criticality, as well, paradigmatically shown in this model. Separation of timescales I've mentioned. There's internal interaction because particles are being redistributed. There are thresholds. So the thresholds I just mentioned, the Oslo model is picked at random. And the observables, well, initially maybe the intention was to have proper correlation functions, but it quickly boiled down to avalanche sizes, durations, areas, radius of duration, things like that. I think now, as a key observable, you find in pretty much every paper avalanche sizes and durations. Okay, now today, self-organized criticality is maybe defined at least, let's say, as I would define SOC today, I would make stronger reference to condensed matter. So I would call it a slowly driven avalanching or intermittent system, and that touches on Henry Genson's definition. He introduced that notion of slowly driven, interaction-dominated threshold systems. Yeah, they're slowly driven, intermittent, so they display some sort of avalanching. You drop a grain and you see a large, or maybe a very small, relaxation, and you drop another grain, you see another relaxation. Nonlinear interactions that display non-trivial power laws, because if they are trivial, well, then normally we understand quite well where they're coming from. They're not very exciting. Non-trivial power law correlations. There's a cutoff by the system size, so you will expect to see some finite size scaling. And the whole behavior is very similar to ordinary critical phenomena, just that there is no apparent tuning of any parameter. There has been an awful lot of discussion in the literature about whether running an Ising model at TC is an instant of self-organized criticality, because, well, it displays some sort of critical phenomenon, and just because, well, it's not tuned because you have tuned it already to the right value. But I think this is a bit, that discussion is a bit lame. The point here is that the system apparently finds a critical point, finds its own critical point. Ideally, there is another system that you can tune. So there's some sort of control parameter that you can set, and then you see a certain behavior, maybe a quiet phase where not much happens, and an active phase where a lot happens. I get back to that later. So if you've got this sort of link between a self-organized critical system and another system, then it's much more apparent that there is some sort of self-organization going on. In the field theory that I'm going to mention, there is, you can see it precisely why the system picks this particular point. So there is, this is the self-organization and the link to classical critical phenomena. And why is self-organized criticality important? Well, because it would be an explanation of emergence. So sometimes we see large-scale phenomena appearing spontaneously in nature, and maybe self-organized criticality offers an answer and offers a mechanism as to why they appear spontaneously. So cooperative phenomena, long in time and space, and signaled by power laws. Yeah?
So these power laws are always detected in these avalanche.
Yeah, now, well, you say always. So I've got a PhD student who I asked, why don't you just measure correlations? Now we've got so much CPU time and some CPU power, why not just measure them? And you can measure them, and it's really nice. Again, I do this with a background in field theory, so you can see what should renormalize, what shouldn't renormalize, where you should see a non-trivial power law, what should be trivial, and so on. So you can see it in the correlation functions now. I'm not going to discuss that much here. And well, once you've got the link to critical phenomena, classical critical phenomena, then there's also the belief that there's universality, and universality offers some form of justification as to why we are studying Mickey Mouse models. So if you want to understand, that's the idea. If you want to understand earthquakes, then you can do that with a tabletop experiment or on your computer, because the physics, the underlying symmetries, whatever characterizes the particular action, that is maybe contained in a much simpler system that you can put in a computer, whereas the real phenomenon is happening on hundreds of kilometers, so on a scale of hundreds of kilometers. So universality is probably the strongest driver for this type of research. Right, now let's move on. I would like to touch on a couple of experiments. This is really just a list of experiments. When I wrote up the book, I went through the literature and tried to find typical experiments that have been done in the context of self-organized criticality. So Kim Christensen kindly gave me this photograph of their rice pile experiment that's going to feature in this list. So very early on, earthquakes were suggested by Baktang and Wiesenfeld as an instance of self-organized criticality. And they were quite brutal. I mean, Bak was not particularly kind with his audience. Very often, he was very abrasive. And he would then cut into a particular field by saying, what you have been doing for the last 150 years is completely useless. This is the answer. I mean, there's a famous book review in Nature where he says, are biologists too, I don't know, to what, to do biology? Does it not take physicists to take biology? And he made similar remarks about earthquakes and similar remarks about evolution. So this was his way of selling the idea, to say, okay, this is a bold claim, but look what it does. And I mean, it is quite amazing. You've got this power law behavior of the Gutenberg-Richter law, and you've got similar setups in self-organized criticality that display similar exponents, so maybe there is a link. So earthquakes is one nice example. Then there were the sandpile experiments, and that already points in a direction that maybe wasn't intended by Baktang and Wiesenfeld, because I get to the forest fire model in a few moments. Some of these models are named by their appearance. They're not meant to be models of sandpiles. The sandpile model is not a model of sandpiles. It just looks a bit like a sandpile. The forest fire model is certainly not a model of forest fires, and it was not intended to be a model of forest fires. It was intended to be a model of turbulence. But somehow it was introduced in the literature as, say, the forest fire model, and was picked up as a model of forest fires. It's a bit like saying that this plum pie model of electrons is a model of plum pies, but it's obviously not a model of, it just looks like a plum pie. So sandpile experiment, very early on, there were some positive and some negative findings. So initially there was a suggestion that maybe there are power laws in these sand piles. Later on there was some negative findings that you see periodic behavior. And I mean, there's a certain publication bias. Obviously, it's very difficult to publish a paper that says, yeah, we tried it and it didn't work. It's much easier to publish a paper to say, okay, this is the power law we found. So the literature doesn't have an awful lot of papers on experiments that failed to display self-organized criticality, which is a pity.
The 1989 paper was one of those, right?
Mm-hmm. Exactly. So then there's experiments in superconductivity. I've got a few more. The rice pile experiment that I just mentioned, this one here, where you get power law behavior for one type of rice and not for the other type of rice, which is a bit weird. And there's this the rain statistics, precipitation statistics by Peters and Christensen, and they worked on this, have been working on this for a long time. So every now and again, they look at ever increasing areas with ever more data, and they find really beautiful critical behavior, but maybe not necessarily self-organized. So particularly more recently, Peters and Nealon, they published a paper on the idea that maybe rain is just sweeping through a critical point, and that's why you get some long-range behavior, but with a cutoff. This is a matter of interpretation, I suppose. So right, I touched on experiments a little bit. Now I would like to discuss a few models, and maybe you can cut me short to get to the theory more quickly. But initially there were lots and lots of models, and initially in the literature, at least in the late 80s, early 90s, there are lots of papers that say, here's another model that belongs to the BTW universality class. And when measurements got more accurate, these papers turned into, look, here's another model, but it's not in the BTW universality class, it's a new universality class. So initially, in particular, the Zhang model and the Manna model, which both appeared in the late 80s, early 90s, they were meant to be about the BTW universality class. So the 91 paper by Manna makes explicit reference to the BTW model, but it turns out that it's not in the same universality class. So I made a list of a couple of models that were particularly popular. The first model I touched already, I think, hasn't been analyzed that much, not least because it's continuous and it's not easy to analyze the Zhang model. This Dar-Ramaswamy model is directed, and it's very easy to understand why it displays self-organized criticality, and it's got trivial exponents, and okay, so this is solved. The forest fire model doesn't display proper scaling. The Manna model, so this is roughly in sequence as they were introduced. The Manna model, I think, really does display scaling, and I get to that in a moment. Then there's the OFC model of earthquakes, or Lamy-Fedder-Christensen model. There's also some dispute about whether it displays scaling or not, and in what regime. It's a non-conservative model, so the bulk dynamics is not conservative. So below a certain level of conservation, maybe scaling breaks down. There's the Buck-Sneppen model of evolution. That's also not clear whether it displays scaling or not. Maybe it requires some tuning as well. There's the Zaitsev model, Sneppen model. The Oslo model belongs to the same universality class as the Manna model, which wasn't immediately realized. It took some time. Sneppen and Nakanishi, I think, they published a paper saying, okay, actually, you know what, the Manna model and the Oslo model are in the same universality class. And that's a good sign. Because if two models are introduced in literature, and then the link in terms of universality and is found a bit later, I mean, that's a good sign. A lot of these models have small, tiny little variants, and they then belong to the same universality class. But hey, if it really, well, what do you say the Americans have this saying? If it walks like a duck and it quacks like a duck, well, it's probably a duck. Yeah, that's precisely what happens for some of these models. But the Manna and Oslo model, they are really quite different, and it's nice to see that they belong to the same universality class, at least numerically. And, well, more recently, analytically as well, if you believe in the field theory for the Manna model. And finally, again, well, I say again, the directed models, but the directed models are touched here. There are now many, many, many different directed models that run under very many different names. They've all been exactly solved, and they are not overly exciting. So this is understood.
What is alpha?
This is the level of conservation. It's not an exponent. So here is, maybe I should go over this very quickly. Here's the initial definition of the Buck-Chen-Tang forest fire model, how it was introduced as some sort of model of turbulence, and it was about non-conservation. The idea was, while sites are either occupied or empty, so an occupied site here is green, like a tree, and empty is black, and if a site can also be on fire, so the tree burns. That's why it's the forest fire model. And in each time step, the fire spreads to nearest neighboring sites. So you can see this fire spreading through this set of sites here. So it slowly moves, the front slowly moves through the system. And at the same time, with a certain rates, trees regrow. So here, this tree was just planted with a certain rate, Poissonian rate. And if the trees grow quick enough, and I mean, you know, that's not how a forest grows, right? You don't have a fire front, and then in the back you've got a new tree growing. This is not how it works. You've got, I mean, what happens, I believe, is that a fire goes out at some point, then you've got some new ignition somewhere. But this is a bit weird. So what happens in this system, I mean, this is why this is not a forest, surely this is not a forest fire model, or model of forest fires. What happens in this system is that you get these, well, you can't, maybe it's a bit too quick, you get these spiraling patterns. I mean, if you wait long enough, then you got one big spiral, and the big spiral, the scale of the big spiral is given by this deposition rate of new trees. And that was found by Grasberger and Kanz very quickly after the initial model was suggested. And the conclusion was, well, because you've got a characteristic scale here that is given by this quantity P, it probably has very little to do with self-organized criticality. But there was a variation of this model proposed first by Henley. But to be honest, Henley didn't suggest it as a variation. He suggested his own model. And then a year after Buck, Chen, and Tang had published their model on forest fires, Drossel and Schwabel published their variation of it that fixes some of the problems. And it turns out it's identical to the one that had been suggested by Henley 3 years earlier. So it's now known as the Drossel-Schwabel forest fire model, but maybe it would be honest to say it's the Henley-Drossel-Schwabel model. But then we end up with Jans, what was that yesterday?
Martin Sitter, Rose Janssen, Leguminitis, Keldish.
Approach, exactly. So we call it the Drossel-Schwabel model, and it's the Ising model, maybe not the Lenz-Ising model, I don't know. But it's a Drossel-Schwabel model, forest fire model. In that model, you've got the mechanics of burning down a cluster is instantaneous. So I show you the dynamics. So fire, if a site gets ignited, then it burns out the entire cluster connected to it by nearest neighbors. So this site is on fire, then it instantaneously lights up all the other trees in the same cluster, defined by nearest neighbors. So after that, these trees are removed, and then there's a certain growth that happens with rate P. So you've got a competition between the growth and the dropping of matches. So growth happens most of the time, and then every now and again you light up a tree. The trouble with that is that there are these two different scales: the planting rate, the rate with which new trees grow, and the rate with which trees are set alight. And this competition introduces another scale, and that requires some tuning. For a given system size, you have to tune that ratio very well. So there is tuning involved, and that makes it tricky to analyze. Here's the dynamics, little movie. You can see, so this is now mostly growth, and now you get big clusters that get removed. So every now and again you can see these large patches that are being removed. And obviously it's not homogeneously occupied with a certain density P. It is patchy because trees have been removed in a patchwise fashion. So there was some dispute in the literature about whether this displays any scaling, and I had a paper with Henrik many years ago where we showed that the avalanche size distribution, the cluster size distribution in this model doesn't display scaling. Right. Now, here's my favorite model. You've seen it yesterday, defined in one dimension. It's the last model I think I introduced. The Manner model is defined in one dimension and similarly in higher dimensions by sites that carry a certain number of grains, zero in principle from 0 to infinity. But if a site carries more than one grain, then it has to topple. That means that initially, in the original definition, all its particles that sit on that particular site are being redistributed to randomly, independently chosen nearest neighboring sites. And later on, Dar suggested to make it abelian by removing only 2 particles at a time until the height is below the threshold of 1. So right now, this system here is quiet. There's nothing happening here. None of the sites exceeds the threshold of 1. And now I add 1 particle by the external drive. This column here now exceeds the threshold. And those 2 particles there, they get redistributed to nearest neighboring sites independently. So I pick a random neighbor and another random neighbor. It could be the same in principle.
Also means abelian.
So,
in this context. Yeah,
in this context. So initially, abelian meant that to be very strict, in the original Bagtang-Wiesenfeld model, abelian meant that the final state of the BTW configuration of the BTW model does not depend on whether you first add a particle at site I and then on J, or first on J and then on I. The final state. People then translated that to, it doesn't matter, the order in which you update, with which you update the system doesn't matter. That's slightly different. But for this model, it's because there is no deterministic outcome. You can't say the final state is the same. It's the state vector. So it's the probability density of different configurations. So these operators are either, in this case, it's Markov operators. They have this property of being abelian. They commute, the Markov operators. Whereas in the original model, it's some sort of permutation. The Markov matrix is a permutation matrix, which says if you're in this state, after dropping a particle here, you end up in that state. Right? So they are very particular Markov operators, if you like.
Question, if I understood the Dar paper correctly, you said you have to move the 2 grains to opposite lying sides. So in 1 dimension, you don't have a choice. You give 1 to the left, 1 to the right. In 2 dimensions, you can either do this or move 1, up and 1
so
down.
So there are a couple of Dar papers
Okay.
where he touches on that, and it's correct. Yeah, he initially suggested that move up, 1 up. So there was this north-south rule and the east-west rule, but that was then he also suggested that you could relax that, and it all comes down to how you write a certain operator identity, namely AI squared. AI squared, namely putting 2 particles on the same side, then fulfills a certain identity, namely all the possible states of, if you put down 2 particles on the same side, it's obvious that this side has to relax. And it's all about how you write this identity. You get away with having this correlation between target sides. Right? You would introduce a correlation if you were to say particles can either topple north-south or east-west. That would introduce a correlation. You get away with it. It still works. That's my understanding. I never tried it. But the more relaxed rule is to say they're just chosen independently.
So the more relaxed rule remains.
Absolutely, yeah.
Because for the mana model, it's not true.
Sorry?
The mana model is not abelian.
The original mana model is not abelian. The original 91 mana model.
What was the original rule?
The original rule is to move all particles. So if you've got 3 particles at a site, then you have to remove all 3. And that makes it non-abelian. The reason, so the non-abelianness, if you really translate, it is really subtle. If you translate it to order of updates doesn't matter, then you can see that if you've got 3 on a site, and you have to redistribute all of them, then it does matter whether you first update the neighbor or not. So if you've got 2, let's say you've got 2 neighboring sites, and both carry 2 particles, then it does matter whether first the right neighbor topples and maybe on top of the one carrying 2 particles, then that one has 3 and will redistribute 3, or whether the other one topples first. That really, you end up with different configurations and with different distribution of configurations. And then it becomes very important how you precisely define the dynamics, whether you update in parallel, whether you update in sweeps, whether you update randomly sequential. So it doesn't matter if you only ever remove 2 sides. And the proof runs the same way as in the BTW model. There is a very deep link between the Mana model and the BTW model, and the Oslo model and the BTW.
All these different variants are supposed to still be the same universality class.
Sorry?
All these different variants, abelian and abelian, they are still supposed to be in the same
Yeah,
universality.
it is a bit harder to characterize numerically the non-abelian version of the Mana model. It is a bit trickier. In particular, with respect to any kind of time, reference to time. The update here, it's fairly straightforward. The natural way to define a time is to say that each side that exceeds the threshold decays with a certain Poissonian rate. If you've got the non-abelian version, then all of a sudden it matters what order you choose, and so you have to be much more specific as to how you update the system. So I'm going to talk a little bit about the numerics. So hold on a second, let me finish this.
So this is the abelian version.
This is the abelian version. The abelian version now, this one topples. It happens to topple, two go to the left, and now I think they're going to split, if I remember correctly. Yeah, that's another possible outcome, right? And now they're going to split again, I think. Yeah, here we go. And one particle is being dissipated. Again, they've got dissipation at the boundaries. Maybe unfortunate. Okay, so now you can see that you don't see anything. So this is a green spot is now an occupied site, and I'm updating this as I speak. And you don't see, there's no patches or anything. It's not overly exciting if you look at this level. So only if you start analyzing avalanche sizes and maybe durations and things like that, you get to see something that looks appealing. Right, so here's a collapse with the Oslo model. Initially, we had this plot, a comparison between the Oslo model and the Mana model. So exponents were the same because it was driven similarly, but boundary conditions were different. And so as a result, you get a slight mismatch, and I was quite puzzled for a long time. I was puzzled. So in the inset, you see a mismatch between the probability density function for the avalanche sizes between the Oslo model and the Mana model. It's hard to see, but there's a mismatch here and there's a mismatch there.
In which dimension is
this is, I think, in 1.55. This must be in one dimension. Yeah. Oh, so this is boundary drive. It's not uniform drive, boundary drive. So in your setup, it would be the exponent is 1.11. Doesn't ring a bell?
The bulk drive.
For bulk drive,
This is driven at 1 point.
At 1 point, yeah, exactly. So you get 1.55 because the Oslo model was originally defined that way, that you only drive at one end. But Mana model was originally defined by uniform drive, so you get that somehow this exponent tau is enslaved by the driving. The exponent.
So if you change the nature, if you made this uniform driving, that exponent would change.
Yeah. Then it's 1.11 for both of them.
And that's the one that Caillou talks about?
Yeah, if implicitly, yeah. So you get this mismatch if you haven't got the right boundary conditions. But it took me some time to realize that this is a matter of boundary conditions, and once you fix the boundary conditions, you get the right behavior, So you get a nice little collapse between Oslo model and Mana model. Okay, so now then a couple of years ago, I met Nguyen Huyen, and we decided to run a large-scale computer simulation on different lattices. So we did computer experiments on the simple chain, the rope ladder, this one, the nearest neighbor chain, the Futatsubishi lattice. So that's interesting. So this is two. You can see how it's constructed. This is apparently Japanese for two rhombuses chained together. So these 4 different one-dimensional lattices, call them one-dimensional, and 8 different two-dimensional lattices. The reason why we looked into this is because it looks a bit tedious, but it has never been done before. The classic outcome in statistical mechanics, classic result for the easing model is that it doesn't matter whether you put it on a triangular lattice or on a square lattice. You get the same exponents, you get a different critical temperature, but you get the same exponents. And we wanted to somehow reproduce that for self-organized criticality and really use the weirdest lattices we could come up with. So we tried these 8 different 2-dimensional, 4 different 1-dimensional systems, and 6 different 3-dimensional systems. And while you can't really see it, these are all the exponents we measured. And within each set, so this is 1 dimension, this is 2 dimension, and I'll show you the 3 dimensions. Here's the 3 dimension. These results are all consistent. So it really does display robust scaling, and it doesn't matter on the details, as you would say. Okay, we haven't done something anywhere near this complicated or extensive for the Oslo model, but I would believe that it behaves similarly.
I mean, it's not always true that the lattice doesn't play a role. For instance, if you have an antiferromagnet, it matters.
So frustration, fair enough. Once you've got frustration, you wouldn't have that in this model. So I could challenge you and ask, can you come up with a 1-dimensional, somehow decorated lattice that doesn't belong to this 1D universality class? I wouldn't think so. Okay, now this is a very, very short chapter. I don't know how my timing is. Right, I better speed up. Very short chapter on universality classes. I mentioned an awful lot of this already. Let me see. Well, so these are the universality classes that I think are pretty widely accepted. So they are the directed sand piles, and the directed sand piles are really completely understood, even though there are about, I would think, 30 or so different variations on directed sand piles. They can be categorized very, very easily and very, very easily understood. So tick this off the list. It's not overly exciting because typically there are no spatial correlations. So, and this is really, I don't think this is fantastically exciting. Mana universality class, that is great because in that book I've got, I think, a page of just a list of models that all belong to the Mana universality class. And there are some of them are deterministic. And that is really neat because you don't have to have that randomness. There are models that produce the randomness internally by some sort of chaotic behavior. So you've got randomness inside and everything, or looks by definition, it looks perfectly deterministic. That is really neat. So Mana universality class, or call it Oslo universality class, call it Quench-Edwards-Wilkinson, call it CDP, whatever you like. This is a very nice big class, and it's understood that the upper critical dimension is 4. Numerics say that. Field theories say that. So this is fantastically well understood.
Can you just give an example of deterministic?
But the train model. The train model is it's very closely related to the OFC model, where I think you pull a 1-dimensional arrangement of blocks and springs over a rough, not a rough surface. So there's no disorder coming in. To be honest, I don't remember all the details. But there's a paper by Paczewski who suggests that the train model belongs to that same universality class. I think they call this universality class the linear interface universality class. So then there's the BTW universality class, if you like. Some people say it displays some level of universality. Some people call them multi-scaling. Others say just no scaling. But fair enough. So some people say there's a BTW universality class, and I'm a bit skeptical about that. The OFC model.
So the BTW doesn't have a large exponent?
No, not if you try to. Yeah, it sounds cynical, but not if you try to measure it. If you make it bigger and bigger and bigger, you would see that it just slips away. So if you measure let's say you measure the exponent on the basis of 10 different system sizes, and you've got a nice little error bar that somehow captures all of it, makes perfect sense. If you take the next bigger system, it will not quite in there. So there is an awful lot of literature about the BTW model and its supposed multi-scaling behavior.
There's no dynamical exponent either.
No, not that I would know about it. So then there's the OFC model. But there are many different variations of the OFC model. It has been understood very well, not least by Middleton. Some people say it displays scaling, some people say it doesn't display scaling. I'm a bit skeptical about it, not least because I wouldn't know of any other model in this supposed universality class. And then, now we're getting down to models that are representatives of their own universality class. I wouldn't know of any other model in the forest fire universality class or the bug snap universality class, if there is any. If I was to draw a line, then I would draw the line here. So maybe there is. So my personal view is, maybe there is self-organized criticality, and it's a universal phenomenon in the sense of there is universality to it. But then maybe the Manner universality class is the only universality class of isotropic systems that exists. So Manner is maybe everything.
But I'm confused. BTW is related to spanning trees, right?
Yeah. And there has been really nice work on that, not least by I think by Ruel and I think is it Seng about logarithmic field theory, 2 dimensions. Really nice stuff. This is all about correlations, and it's beautiful, but it doesn't relate to avalanches. So it's about correlations in the configurations, and that's nice in its own right.
The dynamic one is not the dynamics. You said it's not dynamic on this point.
As far as not one that you could pin down.
Because we have a conjecture that this dynamical exponent is we have a conjecture for this dynamical exponent.
You're probably right, because you will find a model that
doesn't exist, and the conjecture doesn't.
Yeah, I would be very skeptical about the BTW model. I've seen it in action, and I've seen the numerics, and it is just a pain.
So this would not exist in the conformal field theory, these operators? You would have additional logarithmic corrections which make you believe that you...
Correlation, you're saying, is correct.
Yeah, correlations, yes. Yeah, that's understood, but not avalanches. So as soon as it comes to the dynamical behavior, to any kind of updating, I'm not aware of any analytical work to pin down the exponents. Right, so here are the directed model. I promised you to cut that short. I'm going to cut this short. Maybe here's one remark, quite interesting. If you go through the literature and ask, is there a mean field theory, just a mean field theory for any of these models, you will find that actually there isn't an awful lot, because most people associate with mean field theory instantly some sort of random neighbor, there's no spatial structure theory. But then you throw away this dissipative mechanism, and some authors then reintroduce the dissipation at boundaries by having some sort of bulk dissipation. So random neighbor model with occasional bulk dissipation. I don't think it has to be like that. And in the field theory I'm going to discuss, you get the mean field theory at tree level, and there everything comes out, and you can understand what's actually going on at mean field level very, very easily. So that's interesting to notice. A lot of insight has been gained by these random neighbor models, but they ignore space completely, and maybe that is not necessary. So here a couple of analytical tools I would like to touch on. So one relation to self-organized criticality that was made very early on is that to interfaces. And the suggestion was that under certain conditions, maybe you need some anisotropy, or maybe you need non-conservation. There is generic scaling in this type of Langermann equation. So there's a noise term back here. There's a slight anisotropy in this particular example. I just took that. And so that was suggested very, very early on in the late 80s, and then was refined a bit further. And the statements that you can get out of this, this is very interesting, and I would think this is precisely the right direction to take self-organized criticality. But it took the wrong turn at some point, because when it was introduced, this type of perspective by Hauer and Carter, Greenstein, Lee, and Sachdev, they realized that there are also non-conservative models that supposedly display self-organized criticality. And that somehow spoiled the whole story. And there's a little note added in proof, I think at the end of this paper here, a PRL, 1990 that says, okay, we recently became aware of non-conservative models of self-organized criticality. If that is really true, then either there are two different mechanisms to generate self-organized criticality, or our unified approach here is wrong. And somehow this led to the whole direction to die out, and it wasn't followed up after much, much later. So this is really unfortunate, because I think that was the right way to describe these models.
So this is just a generic line dynamics.
Well, there's some, yeah. So this is, at the moment, it's linear, and you can analyze it very easily, but you can also introduce nonlinearities, and then you get non-trivial exponents. And it was all about conservation in the bulk.
But if you introduce nonlinearity, then in the most simple case, if you have phi cubed in this equation, then it's just phi to the fourth theory.
Yeah, the dynamical with this. So the noise has to be conserved as well.
Okay.
And you need to have you have to have conservation, right? KPZ. You can have conserved KPZ, and some people suggest conserved KPZ is in self-organized, or some self-organized critical systems belong to the conserved KPZ. So you have to have conservation, and you have to have conservation in the noise. I could give, not spontaneously, but I could look up the precise conditions under which this type of equation displays spontaneous or generic scale invariance. So this is what they call this behavior. But I think the most popular one is to have conserved noise and anisotropy. And the anisotropy in this system comes about because you need to have open boundaries. And the idea was to have sand grains rolling down a slope. So this introduces the anisotropy, a certain direction. It's the grain.
The noise is isotropic, or otherwise
But conserved.
Yeah.
Right. Maybe I should skip this as well. Okay, so here's one direction I have taken to analyze self-organized criticality, and that was to map the Oslo model to the Quench-Edwards-Wilkinson equation, and then make the link to Pierre Ledussal's and Kai Wies's work. So the idea here was to write down an equation of motion, but not for the let's say the actual configuration of the system, but for the number of charges each site receives. So this is a different interface. It's not the interface of configuration. It's the interface that somehow counts how many charges a site has received. And this is an interface or membrane that travels in space, and it travels only in one direction. So if you put down a grain somewhere, then that site has received another charge. It's like pulling the interface at that point. And as a result, the entire interface might move. And that the movement of the entire interface, the difference between two interfaces, that gives you the avalanche size. So and there's a one-to-one mapping between the configuration of an interface like this. Sorry, it's not a one-to-one mapping, but from the number of charges a site has received, and knowing the initial state, you can determine very easily the current state. So there is a nice link between this particular way of accounting for avalanches and the actual configuration of the system.
Is it the same as saying the number of couplings?
Yeah. So it's not exactly the same, because on top of that goes the noise. Because you've got this variation in threshold, the number of topplings cannot be determined. Without knowing what the threshold is at the moment, you cannot determine the number of topplings from the number of charges. So there is a similar equation you can write down for the model, but Mana model, but it's ridiculous. So I tried this as well. So do it for the Oslo model, and out comes the Quench-Edwards-Wilkinson equation. The Mana model doesn't offer anything like this, because you then have to account for all the randomness that may have occurred when particles were redistributed. So if you've got a site and the direction of particle redistribution is decided at random, then in order to determine how many charges a neighboring site has received by a given side toppling, you have to know the entire history. So this leads to a really strange Langevin equation in this language. But now I'm going to talk about a little bit about what I've done more recently. Maybe actually, to be honest, I should touch on this very briefly. So there's one very popular explanation of self-organized criticality. So I'm jumping subject now. So it's the absorbing state mechanism. Absorbing states are fairly well understood in the literature. There's directed percolation universality class. So actually, it's been a subject for 40 years or so. It's very well understood, I should say. The idea to understand self-organized criticality in terms of absorbing states was to say that the activity in a self-organized critical system that experiences a transition from an active phase to an inactive phase. So while the avalanche is going, you've got a certain fraction of active particles in the system, and when it's quiescent, when nothing is going on, then you are in an inactive phase. The dissipation at the boundaries reduces the particle density in the system. So whenever you lose particles, obviously the particle density is reduced. And this reduction of particle density goes on until the system is inactive. When the system is dead, there is nothing going on in terms of particle reduction anymore, because there's nothing that transports particles to the boundaries. And the external drive, at the same time, adds new particles and therefore increases the particle density. The basic idea is that this particle density has a critical point, and by the very setup of the system, you kick the system into an active phase where this zeta here, the particle density, is fairly high, and then because of the dissipation happening at the boundary, the system slowly slips into the inactive phase when it's dead again, and then the external driving will kick it back into the active phase. So I've got a little cartoon here. So this was the picture. You've got so the external driving rate is h, the dissipation rate is epsilon. So the system sits, let's say, initially here. Then the external drive kicks in and pushes the system slowly into the active phase. Now it starts dissipating. That reduces the density of particles in the system until you slip out again, and then you push it back in again through the external drive. And as you increase the system size, you stay ever closer to this critical point. Well, so I'm not a big fan of this explanation, because I think, well, it's some sort of linear mechanism, and if you look at the finite size scaling, then you need to tune again this external drive and the dissipation very, very neatly in order to make sure that you stay close to this critical point, because otherwise you have non-universal exponents. If you just choose any kind of scaling of the external drive and the dissipation rate, then you end up with arbitrary exponents, and that's not what we are seeing. We see universality. So the truth is that for finite systems, it looks more like this. The active phase, you've got this little foot here. Well, everyone has seen this in a critical system, in a system supposedly displaying critical behavior. If the system is finite, the transition is smeared out, and so you end up with this explanation. You end up close to the critical point, but not exactly to the at the critical point.
What is on the y-axis?
So this is the activity. So the activity, density of particles in the system, and as you increase the density of particles in the system, you get more activity. In the Manner model, if you go beyond, say, 0.9, I think not 0.9448, then the system pretty much runs forever. Even though it's not filled up to the top, it will, on human timescales, run forever. So that's the basic idea, that this is precisely this critical point. Okay, now I'm going to talk about briefly my suggestion for field theory. And one point I would like to make early on is that I think that the natural way to study self-organized criticality is with cylindrical boundary conditions. And that comes about because, so when I started writing down this field theory on the basis of reaction diffusion processes, it's the tree level drops out very quickly, comes out very quickly and very clearly. And then the question is, how do you get finite size scaling? Because that's the only scaling you can ever see in self-organized criticality. The claim is the system finds its way to the critical point. So if you want to now measure exponents, then the only scale that is available is the finiteness of the system. So how do you control that, and how does it sneak in into the field theory? Well, it's through the propagator. And if you've got open boundary conditions, there is an effective cutoff in the smallest k that you can have, in the smallest wavelength that you can have in the system. So the cylindrical direction still has k equal to 0, but the open direction has a smallest k, namely, say, pi over L. So that pi over L, L being the number of sides in this direction, that gives you a natural scale in the propagator, and therefore allows for proper finite size scaling. So I have that again in a second. Here is the propagator, the typical structure. And now this k squared cannot be 0 in these systems because there is a smallest k. And the smallest k is just pi over L. Well, the smallest k squared is pi over L squared. And with that handle, you can then start analyzing it, at least on tree level, very, very nicely. And you get finite size scaling automatically. And the reason why I set it up this way is because initially I wasn't quite sure whether I would reproduce what I know about self-organized critical systems when I go straight for bulk behavior. So this is for finite systems, and it makes an awful lot of sense. So I introduced here a mass as well. Sorry, I put this inside the bracket, but that doesn't really matter. So the mass here, this R0, is now, the role of the mass is played by the smallest k that you can have. So at least that makes a lot of sense, and it's beautiful.
So this is diffusion, right?
Yeah. So at tree level, this is just plain diffusion. That's the bare propagator. There's no renormalization of it. And activity, or the response propagator, so you drop a particle and you see what happens. That's precisely this guy here. There's nothing else that happens.
Why do you drop k equals 0?
So if you want to have these sort of global measures, so if you want to analyze avalanches, then you need to choose, you need to take the space-time integral over the activity. So I didn't really tell you all these details, but this is the activity propagator. You put down a particle, you look at the response.
It's because the grain are falling out from the boundary.
Yeah. So you don't have k equal to 0. So in order. So the eigensystem is just sine functions. That's not. Yeah, does that make sense?
Yeah.
But you want to see if the only cutoff is coming from the system, whether it's self-organized or not.
Yeah.
If the mass is coming from.
So I want to see that L runs the game. I can drop R0, and R0 is equal to 0, so there's no mass. I had a slide about the mass, but it doesn't really matter. Come on. R0, I said R0 equal to 0, and then I can see that if I really push it, I really want to go for it, then the smallest k I can ever get is this one. And therefore, the mass is replaced by the smallest k. I mean, this is finite size scaling, as we know in 5-4 systems. I mean, this is well understood. But to see it somehow at work in this system was at least quite satisfying.
But what is the relation? I mean, I'm not familiar with that, but I mean, what normally field theory you start with a Lagrangian or Hamiltonian, and you have a field, and the field describes something. So what is it here?
So here it's in the language of second quantization, you've got creation and annihilation operators, okay. And there are two different. I get to that in a second. There are two different species of particles. You can either have active particles, and they propagate in a certain way, and you've got what I call substrate particles. They just sit and don't do anything. So their propagator is essentially this with d equal to 0, but then you have to regularize things and introduce another mass term. But that's just a matter. I mean, you know that in quantum field theory, you have to sneak this in every now and again. So these creation and annihilation operators, they allow you to, let's say, drop a particle somewhere, and at the same time, the annihilation operator allows you to count particles somewhere. So that allows you to construct expectations of, say, the density of active particles at a certain point in time and space, given that you've dropped an active particle at an earlier point in time and at a different point in space. So it tells you what you expect in terms of activity somewhere else in the system, given that you drop a particle somewhere. If you take the integral over this, say you've got a setup of a certain substrate configuration, and you drop a particle somewhere, and you take the integral over this activity, the propagation of activity throughout the system, you take that integral in time and space, then you get the avalanche size. The integral over time and space of the activity gives you the size of the avalanche, the number of topplings. So that makes the link back to the classical observable in self-organized criticality.
You're going to show us some action?
I'm not going to show you the action, but I show you the vertices. Come on! I show you the vertices, and from the vertices you can reconstruct the action. I threw this slide out because I thought it would be too technical. It would be too. I can't know. So here's one nice little insight also that came out very, very early. So this is an early slide. I was so happy to see this. If you introduce open boundaries in only one direction, everything else is periodically closed, then you get these very, very nice relations straight away, and for nothing, no investment needed. You know instantly the average avalanche size, because you know that that's another nice insight, that the diffusion constant D does not renormalize. And to this day, this is a pain for me to implement. So D doesn't renormalize, but there is a field renormalization because you get from loops, you get contributions to I omega. So you've got field renormalization, and therefore there is Z is not trivial, but the Z does not come from the renormalization of D. It comes from the contributions to I omega. So because it's the way you can see that there's no renormalization of D is this, very simple, straightforward. In the Manner model, if you distribute particles to randomly chosen neighbors independently, then each particle performs a random walk all by itself. So if you look at the trajectory of a particle, that trajectory will be a random walker trajectory, even though it has associated with it its own clock. Every now and again it gets stuck, but then it's reactivated and continues. So if you ignore the clock, you just look at the trace, then you see a nice little random walker trajectory. On that basis, you can calculate the average avalanche size and other properties. The point is that you would see that it's all governed by the same D. So you can see that D cannot renormalize.
Yeah, so in the interface mapping we have, this is equivalent, I think, to the statistical symmetry for the interface.
Okay. That's good
also
news.
Meaning the elasticity of the interface is that
Okay, that's good news. Very nice. Okay, so go through this here. Okay, so here are the vertices. So the red line, I read it from right to left. The red line is the propagation of an active particle. And here is this branching that happens when an active particle. So this is, I have to say, this is a vertex that is recovered not straight from the action, but by looking at the renormalization. This is being generated by other vertices. So you end up with a theory that at least contains those four. So this is what happens here is that a particle effectively branches into two particles, namely by hitting another particle on the substrate. So active particle comes in, sees an inactive particle sitting on the substrate, and effectively splits into two particles, so produces two active particles. So you might wonder, actually, if you know this sort of reaction diffusion language, you would think that this requires an interaction with a substrate. But I've shifted the substrate density by a half, so that at mean field level, the critical density of occupied sites is a half, and all you get to see is a branching process. Particles come in, hit a site, and if that site is occupied, then they branch into two, and if the site is empty, they get stuck. So you get a critical branching process at mean field level. I've shifted this by a half because it's much more convenient. So at that level, I've got this simple, seemingly spontaneous branching of particles. Equally spontaneous is that a particle produces two inactive particles. So it finds an inactive particle, so it produces another inactive particle that is here. Here there is a now interaction with a substrate. Particle comes in, and now this is effectively mass generation. This particle here, when it comes in, probes whether there's a particle sitting on the substrate. And if there is, then it carries on. And if there isn't, it doesn't carry on. So this vertex comes with a minus sign, and it probes whether if there is no particle sitting on the substrate so that it can carry on its nice little trip, then it gets stuck there. So this is a mass term. And there's an equivalent vertex where a particle comes in, finds that there's nothing sitting there, and generates a particle on the substrate. So the green wriggly lines are substrate particles that are immobile, and the red lines are active particles. And you've got the symmetry between the vertices. And I have to say, there's a slightly bigger story to it. And we can.
So there are different thickness of lines there?
Yeah, unfortunately, but that's just no. Forget about it. This is not intended.
The activity field, which is the red.
Yeah, activity field and substrate field. The green
propagators, I mean, you showed us one, which is diffusive.
The one that is not diffuse is 1 over minus I omega plus epsilon. This epsilon is just to regularize things. If you like, it's 1 over minus I omega.
That's the green one.
That's the green one, yeah. That's so getting stuck. So I haven't told you this, but there's one vertex that comes about because of this particular construction. This is really unfortunate and a true pain in the neck. So it's this one here.
1 over I omega is something like the conductivity of a superconductor. Is there any
Not that I would know about it, sorry. So it's this one here that proved to be a complete pain. So this is one particle comes in. This contributes to the renormalization.
These are your active ones.
Sorry, this one generates pair annihilation. So two particles come in, or coagulation. Two particles come in and generate leave as one particle. This one contributes to this one here. If you look at it, so this is a 1 over minus I omega. This is another 1 over minus I omega, and this is 1 over. That's just a normal propagator up here. If you integrate over this, this is a ridiculous divergence, and this cannot be dealt with. It took me a long time to understand how to deal with this vertex. So I have to say there is a bit more to it, but you can see an awful lot from these vertices already.
It appears in functional RG, it would be an offset of the critical force. It's non-universal, and you somehow have to subtract it.
Yeah. So you do an additive renormalization?
The Kirch field. Yes.
So because of the symmetry, each of them has a corresponding term. You can always replace the nose, right? There's always this symmetry. Whenever you see a red line, there's an equivalent vertex with a green line coming out. So you've got another one like this. And at least to my understanding, this makes no sense. But these are technicalities. We can talk about them later.
But that symmetry is there in your action.
Yeah, that symmetry must.
See the action. I mean, it's secret.
Yeah. I get to that. I know not in this talk. It's not secret. No. I mean, I have to say, I've been struggling this for many years. Truly, for many years. I would like to finish the exponents off, right? And one reason why I'm so keen to finish this off is because I haven't got any disorder. It all comes out from this natural action. If you do it at the level without any continuum approximation, it's exact. It's an exact representation of what you're doing in the Manner model. Every single term that you look at has a corresponding event in the numerical simulation, so you can really see things.
Once the Martin-Sijaros formalism, what we have read about disorders, there's no more disorder, and you can also trace the events.
Yeah. But okay, but it's not a functional RG. I'm not, sorry, maybe you misunderstand. I'm not considering this as somehow better or worse. I just consider it as really different. And
it's equivalent in some way.
Yeah, I would hope so too.
But
This is not CDP field theory. It's different from CDP.
Yeah, it's different from CDP because what you would write down in terms of a Langevin equation for the substrate really does look different.
Well,
and I cannot.
We have
Sorry?
not seen any difference yet, I think.
Yeah, I get to that. But we can get to that later, maybe. Okay, so at tree level, I can at tree level, I recover the mean field theory. So if I run simulations at, say, dimensions greater than 4, because at 4 I expect to see logarithmic corrections, so I go to dimension equal to 5, I know that what I should see in the numerics should correspond to my tree-level diagrams. So I've done that as well, and the scaling comes out pretty much automatically. What is interesting are then these prefactors, and you can construct very easily universal amplitude ratios. And I've done that, and here's a comparison. So because there is no renormalization of the diffusion constant, this one here, the average avalanche size, that comes out exactly, but and this is not a big mystery or any kind of confirmation. But a universal amplitude ratio with the right boundary condition, that is much more interesting. So numerically, the correspondence is not perfect, right? There's a bit of an error, but I'm quite confident that I got that one right. And then for higher order amplitude ratios, it is much better. I think one reason why it's difficult to really fully recover in the numerics what I find analytically is that numerically I haven't got fantastically big systems. If you are in d equal to 5, then having a system size of, let's say, L equal to 100 is already ridiculous, right? L equal to 100, it's 10 to the 10 sites. It's not doable. So you have to stick with really, really small systems, and then boundary effects play a big role.
Okay, so these numbers are not consistent with 1 over S, the distribution 1 over S to the 3 half times an exponential.
No, so because I've got one open boundary, what really makes the music now is precisely the scaling function, and this is not an exponential. No.
Do you know what it is?
No, I only know these ratios there. It comes down to counting trees and symmetries. So if I, maybe. That's. I think I'm running out of time.
We have a meeting which probably can help shape this prediction. We can discuss later.
Okay, so we've got the mean field theory. So now I would like to get to the mechanism, how I think self-organized criticality comes about. So if you just look at tree level, and it just generalizes to loop corrections as well. There's a very simple tree-level contribution to the Baire propagator that comes from the interaction with the substrate. And the wriggly line with the filled circle there, that represents the interaction of active particles with the substrate. So I can write down this sort of Dyson sum where, particle comes in and just carries on. Particle comes in, interacts with the substrate. Particle comes in, interacts with the substrate once, twice, and so on. And I can just sum them all up, and I get my overall mass. And this term here, this bubble there, that contains all these contributions. And the question is, why is that equal to 0? Because if I choose the wrong density on the substrate, because I shifted things by a half, at mean field level, that would be anything different from 0.
Is this a geometric series, or?
Yeah. If I get anything different from 0, then I'm away from criticality. So how come that this term vanishes? And at tree level, it's immediately clear, but for higher orders, the symmetries of the vertices plays a crucial role. So I could also ask, what is the expectation of substrate particles, inactive particles on the substrates stuck there. So this is somehow the lowest order. It's just you look around and you check whether there's a particle. And this is a contribution from the driving. So this open bubble here is a driving. External driving interacts with whatever is on the substrate and leaves a new substrate particle behind. Now, if I ask how many substrate particles are around, then I have to sum over all these terms because I am driving the system. And if I'm at the stationary state, then all of these contributions must sum to 0. So at stationarity, I don't have a change of this expectation. And if I could draw similar diagrams for correlation functions, they are also stationary, and I would get a similar result. So the sum of all these diagrams must be equal to 0 because there is no additional deposition. At stationarity, the density, let's say I'm looking at the k equal to 0 mode here, the density is constant. And because the density is constant, that means that all these must cancel, and they cancel because I make the right choice for this wriggly line with a bubble at the end. So that one here, this guy here, is chosen at the stationary state implicitly such that the entire collection here of diagrams sum up to 0. At mean field level, the choice is wriggly line with the bubble is equal to 0. Then everything cancels. At higher orders, you get a little shift, and therefore the critical density in the Manner model is different from a half. So if you use this symmetry of the vertices, you know that this vertex must be equal to 0 because of stationarity, and therefore, because the collection of all the diagrams in here is identical to the collections of diagrams in there, the mass must vanish as well. So you get this. The criticality comes about because we impose stationarity. If we would look at the Manner model away from stationarity, then there is no masslessness. It wouldn't be critical. So, right. So here's my little summary how I think self-organization works. So the attenuation, that the reduction of the activity level, that's equivalent to mass. Conservation links the attenuation and the substrate deposition, or equivalently, the equivalence between vertices and diagrams links whatever additional deposition you've got on the substrate with the mass of the propagator. And because we've got stationarity, both sets of diagrams must be equal to 0. And I wrote down here terms and conditions apply, because, well, life is never easy, right? Things are normally a bit more complicated. Right. Well, okay, so for example, in the CDP, you've got this funny term, this one here, that at least contributes to, turn the light on again, contributes to the substrate density. That's dt, I think you call it a little n?
Or n, yeah.
N is for the substrate, right? N is equal to, I seem to remember there's originally a minus, actually, a nabla squared phi. And a term like that would contribute, because we had, that would contribute to a change in n given phi. So you get, a deposition that would lead to deposition. That is a net deposition. If you start out with an empty lattice, empty in terms of substrate particles, and you drop inactive particles, then you are left with, in this case, a negative substrate particles sitting on the side where you dropped your phi. So this is, you have to be fantastically careful about conservation when you write down the right-hand side of the Langevin equation for the substrate particles. So there's terms like that are, but at least there must be another term that effectively kills this one off. Okay, so I should wrap up now. No, we'll wrap up.
Sorry, so you're saying that your filter A, which you didn't tell us what the action is,
Now you're really as disappointed, I can see that.
Is a bit different from the CDP, but this belongs to the same universality class, right?
Yeah, well, frankly, I would think that you got it right. So I believe that the Manner model belongs to the Oslo universality class, that they're in the same universality class, and I strongly believe that the Oslo model belongs to the Quench-Edwards-Wilkinson universality class. So if you make the link between CDP and Quench-Edwards-Wilkinson, then you make the link between CDP and Manner. So I wouldn't be too surprised if we find out that it just takes a couple of manipulations to go from my action to your CDP, or not to your CDP, to Rossi and Pastor-Sartoris.
Some irrelevant terms. I mean,
it could well be, fair enough, and I accept that.
I don't know what your action is.
Yeah, I think I got the point, yeah. Okay, so very briefly, if Harvan-Kardar initially said masslessness comes about by conservation, and I say, well, stationarity brings about masslessness. There is a link, obviously, between the two if you've got bulk conservation, because then stationarity corresponds to stationarity corresponds to conservation. But all you need, in principle, to have masslessness due to stationarity is the symmetry of the vertices. So from my point of view, what is the primary cause for criticality in these systems is the symmetry of the vertices. In principle, you can have non-conservative self-organized criticality as long as you maintain the symmetry of these vertices. Here I mentioned this. Innocent-looking processes destroy the critical state. This is one of them, which I wouldn't know how to deal with in my setup. So this would be a real problem, because that would precisely kill off that symmetry between vertices that lead to deposition of substrate particles and vertices or diagrams that contribute to the mass of the propagator. And, by the way, I think it would be really, really nice to link up any of this, your work or this secret action, to the absorbing state mechanism, to understand how they are related. Because the absorbing state mechanism at the moment, I think, is very widely accepted as the explanation for self-organized criticality. Okay, so I ran through this very quickly, my little summary. So I think I've got little doubt that self-organized criticality exists in computer models. I think I'm happy with that. I've seen lots and lots of numerics. I've done lots and lots of numerics. And I think that's really believable. It's big systems, decent numerics, and robust scaling behavior, at least for the Manner and Oslo model. I think there can be little doubt that self-organized criticality, as originally envisaged, really does exist. The question is, does it exist in nature? And then there are a couple of experiments that really suggest so. I mean, I've just wrote a couple of them for which I know successful implementations, if you like. I'm sure there are more. And the analysis for them is very, very impressive. So you would think, particularly the precipitation, has a clear understanding of to what extent it displays self-organized criticality. Whether self-organized criticality is ubiquitous, I doubt it, to be honest. Because, I mean, one thing that I find striking is that the initial claim was that self-organized criticality is to be seen everywhere, and then it takes years and years and years of hard work to do a tabletop experiment. If it is ubiquitous, then it should take 10 minutes. That's at least my naive understanding of ubiquitous. So if self-organized criticality understood, well, I don't know really. I've got the secret action, but I guess we're getting closer. And whether it's worth understanding, well, I've spent an awful lot of time on this. Yeah, obviously I think it's worth understanding. But it is in general, it is a mechanism that produces long-range and long-time correlations. So obviously it has a great appeal, particularly with respect to avalanching intermittent behavior. All right, and thank you very much. maybe I didn't thank you specifically for having the opportunity to be here. Actually, thanks a lot for being invited.
I have just one technical question, just to understand the difference between this type of models and you. So, to know the instant height of the grains at some point, one has to add the number of substrate particles to active particles or not? Because here, if I understood correctly, n is a number of total number of particles, and phi is just a kind of activity which is not number of particles.
Yeah. So in my language, if you want to know the instantaneous number of particles on a site, then you have to add the two, substrate and active. Yeah.
But here it's not like that.
Yeah. Here I understand n is the total number of particles sitting. Yeah. That's why I said this would be a contribution to my substrate.
I mean, it's a the idea
maybe there's a way to get rid of it. I don't know. As I said, I just don't know.
So what is essential? So if you look at some of these other models which don't have SOC, can you see that the symmetry is not there? The symmetry between it's not possible to go.
It took me a while to get to that sort of symmetric set of vertices for the mana model.
Mm-hmm.
I wouldn't.
Like
I
you
wouldn't
can't
know.
just look at a model inside.
And the models are very, very different. I mean, there are many different models. And they really are defined in different terms. And sometimes tiny little details really matter, really make a big difference whether you see or not see scaling. Let's say whether you could come up with models where you pick amongst nearest neighbors, not at random, but depending on how occupied they are already. That makes a massive difference.
Okay, any more questions?